Hello, um, my name is Min-Hsuan Peng, and I'm from Warframe Research. Today's Twitch talk is about improved visualization labeling. In this talk, we will take a look at the labeling system of visualization functions in Warframe language. To be more specific, they are the new functionalities added after version 11. So automatic labeling has been introduced around version 10, first in this plot for labeling points. The automations is on finding the beta location of the labels, so they don't run to each other or points. Since then, we have been extending the labeling automation in other visualization functions. The topics of labeling automation is divided into 4 rows in this marketing page. We will take a look of them together. The first row is the automation added in various charting functions. So let's take a look. So the first one is automatic labeling in bar chart and rectangle chart. This is just an example to show the case that how the automation has been added in this rectangle chart that was introduced in version 7. So the key point that we are looking at here is this line. Chart labels go to callout of an entity list. So we can take a look of the same input without the callout. So this is how it used to work since version 7. Then you can see that the labels by default is put on the bottom of the axis, below the axis. And because of the country names, the lengths are different, they run into each other. So the automations in this case is that they will layer themselves so that they don't run to each other. And the only thing you need to do is to wrap the callout on the list of country names here. Right, so in this example is just to talk about the population GDP for the group of 7 countries. For the same thing, we can do on bar chart. And there is this example is slightly more complicated because that the first argument in the chart labels is for the group labels. So you can see that the group labels has the similar automations like the rectangle chart. They are layered so that they are not running into each other. I also used a callout wrapper on a specific data point to single out an interesting fact that there is no nuclear production in Italy since 1990s. So that is the automations we are handling here. The next example is the automatic labeling in pie chart. So again, pie chart is also was also introduced since version 7. We already have the labeling system for pie chart and actually for all the charting functions. But we always had the problem that the labels will run into each other, especially when the pie slice is very small. In this version, we added some algorithms that they will find the position so that they will try to avoid running into each other. So the same thing is that the same syntax like the bar chart and rectangle chart. The only thing you need to do additionally is to put a callout on the labels. Right. And here is a slightly more complicated case, but the purpose of this example is to show off that no matter what kind of the labels you are using, they will run the same algorithm, and they will avoid running into each other. So this is an example of the passengers in Titanic. And instead of just a bunch of strings, I created the pie chart within the pie charts, and I use the pie charts as the labels. And you can see the algorithm after it is run, the labels are positioned in a way. The next type of chart is the bubble chart. Bubble chart is very similar to list plot, the points. The only difference is that, well, one of the difference is that the bubble chart has various sizes of bubbles. And this created a very interesting task for us to handle the labels. The syntax is just like the previous charting functions. The only thing that we use that's additional is using the callout wrapper on the labels. And here, instead of using chart labels, I'm using labeling function. So let me this one. So this bubble chart is to visualize the countries, and the X position is the GDP per capita. The Y position is the poverty fraction, and the size of the bubbles represents the population. So this is the results, and the benefit of using a labeling function here is not very obvious. I mean, we can definitely we can use the wrappers instead. Just to use the wrappers and the call out on each data point, and here. Then we can have the same output, the same results. And but in the next example, I will talk about more about the labeling function to show the benefit of using that. So GeoBubble chart is a geo visualization that we added also in this round. It has the same auto labeling automation as in bubble chart. So let's see the data. So the things I'm trying to visualize here is the oil production, the petroleum production around the world. I get the information from our entity. And if I just visualized every point here, you will see that there are a lot of bubbles. A lot of countries produce petroleums. But in this situation, if you want to label everything, this plot is going to be very, very busy. So I thought that maybe I could just label the top 10 or, ish countries that produce the most petroleums. So here. Here I'm using the labeling function. The first argument is the data itself, and the third dimension of the data, like I said before, in this case, is the petroleum. So it's the unit is barrel. So I'm only visualize that if the number of barrels is greater than 1 million, then I'm drawing the labels. So this is the results. So labeling function provides you the flexibility to programmatically label stuff, and the automation of like the label avoiding is still done in the interface of callout. So here is the the callout. Right. So these 4 examples is just some representations of what we have done for the charting functions. So that concludes the charting function automation. So next, we are going to see labeling in plots. So let me go back to the top page. So that's the second rule. So the way we organize this rule is by the type of plotting functions, such as the points, curves, region, and then services. So the first one, we are going to look at the point labeling. Point labeling is the first algorithm that we developed for automatic labeling. The first class function is list plot and its family, like list log plot, list log log plot, list log linear plot, and the date list plot of such. The addition to this version is the same algorithm working for 3D points. So this is the 2D points. This has been working since version 10. And now we have improved the speed and the quality of the labels, but it is not completely new. But the new ones is for these 3D points. This is list point plus 3D. So we apply the same algorithms on the 3D plot, and then you get the results. And one thing you can notice that is that it's not every point get labeled, or at least it wasn't placed in the graphics directly. The reason is that our priority of placing labels is so that they don't interfere with the main features, which here is the point. So they are actually put in the tooltip. So I'm not sure if my tooltip goes through the internet, but if you try this at home, you will, and when you mouse over the points, you can see the tooltips that shows the names of the countries. So does the case for the list point plus 3D. So the one thing I want to mention is that, well, I can just show you here. So if I evaluate this list point plus 3D, right? So the algorithm is run based on the snapshot of this perspective, including the view direction, the view angle, and the projection itself. So if I try to rotate it, you will find out that the labels doesn't get to switch the positions, and they started to run into each other and even to the points. So this is intentional, because we saw that it will be very confusing. You know, the labels start to jumping around once you start to rotate. But you may ask that, what if I have a different view angles and view projections? Will the algorithm still run to find out the best positions? And the answer is yes, but it is not doing this dynamically. You have to specify the view angles and view projections in the options of the plot. And we will look more into it in the next examples. So that is for the points. The next one is for the curve. So when we move away from the points, things quickly get complicated. So I mean, instead of saying that we have the full automation for the curves, which doesn't really work that well, because it is very subjective to say that what is good labeling for the curve. So what we come up with is that we need a bit of information from the user to tell us that where you want to put the label. And the automation that is done here is so that you only need to specify the label position, and the leader position is you only need to specify the leader position, and the label position is automatically found based on, for example, that it's not going to run into the axis or not running into the curve itself. So initialize. So this is I use the find maximum to find the local maximum points. So you can see that I only specify that where my leaders should attach to, but I didn't specify. So this is the leader positions, but I didn't specify where the label has to be. And the label position is automatically found in a way they avoided running into the axis, nor running into the curve. Right. So that is the automations. When it comes to parametric plot, it gets even more complicated. And the automations here is that it is trying to find the curves that is the least ambiguous points that we can label. So in this example, right, so they are trying to space out so that the lines is not getting too close to each other and very busy, if it is possible, right? The same thing we did is for the parametric plus 3D. Right. In this case, the automation is done in a sense that we do specify where our label wants to be, because it is quite an ambiguous task to know that where the label should be automatically placed. So we saw that by looking at the plot, usually the plot, because it's 3D, it can be complicated. The user could tell us that where the label should be. And once the label is decided, a leader line will be drawn and point to the closest point of the curve of the in this case it is the curve. But the parametric plus 3D can also plot the curvatures. I mean the surfaces. That is the one after this one we are going to look at. The next one we are looking at is the region labeling automation. The automations that is done here is that when you specify the label position that is outside of the region, the leader line is going to be drawn and point to the closest point based on the geometry. If you specify the label within the region, then there's no leader lines drawn. So this, the first label was placed outside of this red region. So that's why the leader line is there. And second label here is placed within the region of this faded orange. And that's why the leader line is not drawn. For parametric plot, it's the same behavior as the curve case, that it's going to find a connecting point that is less ambiguous. And all these functions, the interface is using plot labels, as you can see here. So the parametric plot is using the plot labels, and the region plot is using the callout. So callout is a wrapper that's not just for the data points. You can also use it on the functions. The last one is the service labeling. like I previously said, for parametric plot 3D case, you do specify the label position, and the leader line will be drawn pointing to the closest surface point based on the geometry. So it's using the plot labels, the callout, and expressions. So the expression here is just going to refer to the expressions of the plot 3D. And this 0.504 is the XYZ coordinates or in the space that you want to put the label at. And then the leader line is automatically drawn. Right. And this is the example similar to above, that you can find the local. This is actually the global maximum and the global minimum. And then you can specify multi-labels used with the callout, and the leader line will be drawn and to point to that. Right. So that is the automations that we added for the plots in version 11. The next rule, which is third rule, is a rule of detail. It talks about what are the parameters that we considered in the algorithms. Like the first one, it showcase the same data set, but with different options. You will see that how labels are displayed. Like when image size is small, and like I said, with the priority that the label is not running into the points, you can see that there's only a few labels shown. But with a bigger image size, you get more labels. Eventually, if your image size is big enough, you will see all the labels. So that is not the only options that we take into consideration. We also take into the consideration of aspect ratio, the plot style about the point size, and also the label style, which you can where you can specify the label size and the font family. Right. For the 3D version, like I said before, we take into we take the view projection, the view direction, the viewpoint into consideration, and you can see that while you specify the options, the label locations are automatically adjusted so they don't run into each other all the points. The next two ones is the next one, this one, the labeling automation scenarios here, they are a bunch of examples that are not very general. They are very specific to the plots, as we have like more than 100 visualization functions. While we are rolling out our automation into each one, we found out that it is not one fits all situation. So we had to modify each plot to have their own spatial behavior. And the first one is for the discrete plot, also for the discrete plot 3D, that when you specify the labels that contains the variable, it will catch the values automatically and label them as the points. While when you specify the labels in the plot labels option, that using the hold form, this hold thing is not going to take the values. So that is the automations, the spatial things that we did for the discrete plot. Right, and this is an extreme example for the parametric plot, where to find the label positions so that they are far away from the other curves, to the extent that they can still be distinguishable that they are their labels. So this is, you know, it may not seem that it is obvious, but the algorithm under the hood is working very hard on finding the positions. Another example that we added in version 11 and beyond is that, like 11.3, I believe, is the feature space plot and the feature space plot 3D, which are the two visualization functions tailored for machine learning visualization. And in these two functions, we also used the automatic labeling algorithms, so that when you put the actual images in, they are not going to be all crowded and block the view of the points. So this is just a collection of different scenarios of the plots. And as we continue to roll out our labeling algorithms to other visualization functions, we will have more things like this. Right. There are a couple, at least a couple options for that is the labeling algorithm related. The first one is the label visibility. It is an API for you guys to specify that in what sense label should take the order. So the first example here is just to, so there are two groups of data. And by default, the labels are ordered, and also, like in the algorithm, they have the order based on the input. So you can see that the ones that is specified after was removed because they don't want to run into each other. But you can specify the label visibility in a way so that it is rendered backwards. So the example here is two data sets. The first data set is the planets. No, it's the moons of the Jupiters, and then the blue data set is the planets. The x-axis is the mass. The y-axis is the radius of the planets or the body. And the interesting point here is that the largest moon of Jupiter is actually larger than Mercury. But in the default view, that information is hidden because of the order of the labels. And the label visibility gives you an opportunity to change that, so we can see, right? This is another example that you don't really need to only have strings for the labels. It can be anything, actually any expressions. In the version 12, comparing to version 11, we have improved our algorithms a lot, and this is the chart of our improvements over the speed. So the last row is a bunch of examples that we saw that using labels in the plots in these examples will create some interesting and useful applications. So the first one is to create the connecting dots game. So do you remember those drawing games that only have a bunch of numbers on the paper, and you have to connect the numbers in sequence to reveal what they are? So this is the process to recreate the game. So let me show this to you. So the sample, so I'm going to show you this. Or before I show you, I'm going to refresh your memory about what is a connecting dots. So this is the connecting dots game. So there are a bunch of points and a bunch of numbers that's for the points are labeled, and the task is that you grab a pencil or something and you connect the dots in sequence. So if you do that correctly, in the end you will see the overall picture, right? So, and when we have the labels, and we saw that this is exactly what this is for, and we should create a game that based on the algorithm. So here, the sample that I am going to use is from our icon entity thing. And this example specifically, I think it's called like a cell or something. And we can use some image processing techniques to extract the images. So first one, I'm going to extract the ages, the age of this image, and I can see that in the graphics. And the problem of listing of the points is that they are not in the order, and we do need the points to be in the order, so that it's not randomly connected. And we can use a built-in function called find shortest tool to reorder the age, right? And I can show you in the manipulate that from the first, so you can see the points is ordered, right? But this is way too many points to label. So the next step is that we are going to downsample the points. So I created a data function that's based on the points, and I'm just going to, equally spaced out the points. And I can show you the new, so if I use this as a point, you will see that this is the point that I downsampled. This is the line, and you will see this is eventually what we hope the user, the player would connect the points to. Right? And in the end, we can just use labeling functions and to label this. So this is it. And if you label them correct, you connect them correctly, then you get this. Right. So you can modify this the sample rate here, right? And then you get a more smoother one, but then you get way too many points. It kind of like defeat the purpose of hiding the shape of the curve. So there's a balance over there. So that's the example. So if you are curious, you can try this with different icons. There are many, many icons in our entity database. So the next example I want to show you, so I'm going to show you the Venn diagram first, because I think it's fun. So the Venn diagram here, well, everyone knows Venn diagram. It is 3 disks. This is the basic ones, and this is the A, B, C, 3 disks. And there is an intersection that is AB, and there's the AC and BC, and there's the intersection of the 3, that's ABC. How do we do this programmatically, so that and ideally we can extend this into the 4 ones, or even more. So here, let me, oops, here. So this is the ABC 3 disks. So we can find the subsets by using subsets, and we can visualize them using graphics, and we see that this is the 3 disks that we want. And the next thing, which is, believe it or not, this is a more difficult one, which is finding the color. These are the colors that we are going to use. And this is the discretized regions that will represent these 1, 2, 3, 7 regions. And in the end, we just use region plot with plot labels that using the callout and putting the labels at the center of each region. So there we go. So with the same spirit, we can do the same thing for the 4 disks. Oh, and they are not necessary to be disks, but they are the 4 regions. So this is what we are going to visualize. And the same thing here, the subsectors, the colors, and in the end, we have the 4 region Venn diagram. Right. Yes, this place. So the first one is the A is the center one, the ellipse, and the B is the right-hand side half disk. C is the bottom half disk, and the D is the vertical one in the center. Right. So that's four disks or 4 regions. So that's the Venn diagram examples. Right. So the 2 other examples in the middles, they are relatively simple, but they are effective in the sense that the input is really is quite short. But like this is a visualization in contour plot to visualize the poles and zeros. Without labels, you have to think about what's the function and what the function is, and to figure out that which one is the poles, which one is the zeros. Yes, granted, there are other ways to visualize, to annotate these, which is by the legend, but it's also possible to just use the call out to label these 5 points, which ones are the poles, which one are the zeros. So the syntax is just using callout on the function, and there's just multiple callout. 1 callout and 5, pole, 0, 0, and 5 positions. So that's as simple as that. The next one is a slightly interesting, more complicated examples of utilizing this point plus 3D to visualize the planets and to label them. So we get the information from the entity value, and also get the orbit path for each planet, and we just use again, we use the callout wrapper to name them, to label the names, and you can see that the names are positioned nicely. And we can zoom in into the inner solar system that that contains only the 4 planets and the sun, and you can see that well, you can see the orbits is not completely on the same plane, and the labels. And if I reevaluate all these examples, the position of the planet will change, of course, because this was created earlier this year. All right. And like I said, you don't need to just use the string names. You can use the images. So instead of the names, I use the images of the planets, and I place them in the orbit. It looks like the solar system. Right. So that is some visualization, labeling visualization examples that we added here. And as I mentioned before, we are continuing roll out the automations of the labels into other visualizations. There are still a lot of things to do, but I think this will help a lot of users to create more content-rich plot. So that concludes my presentations for version 12, improve the visualization labeling. So if you have any questions, you are welcome to raise, and I will see them now, and I will answer them. Okay, so okay. Right, so the question here is that often for the purpose for exploratory analysis, they need to label all points in a scatter plot. I believe it's, in this case, it might be list plot. So the question is, do you have an option for that that would move all the callouts far enough out of the label to label all points? The short answer is no. There is no automation currently that will move all the labels out of the interested region and just to draw very long leader lines. Main reason is that it still looks really bad because all the leader lines will, come across with the points, and in the end, it's just unreadable. But I mean, yes, the question is valid, and we are still looking into the possibilities how we can do this. But like I mentioned before, the points are still actually labeled. They are just labeled through the interface, like the tooltip. It is not printed in the graphics. But yes, we are still thinking about what is better way that we can actually label all of them, or in some other way that they are not directly labeled. So I think in the previous version we had an examples that, so instead of label the full labels that you want, we give it a token and we use the legend to legend the token. Like instead of a full word, we say that this is label A. In the legend, we say what the label A is, right? Right. Right. So we are trying to make labels interface as simple as possible. So it may not seem that there are a lot of factors that can affect it, but as I mentioned in the third row here, there are actually a lot of parameters that can affect the layout and the output of the labels. So if you have time, please read more information in the third row here, and you will find out that by just changing a few options, you may see more labels in the plot. Um, so there's a question here that what is the internal layout method used here? Right, so for the list plot and list point plot 3D, the labels here, that is the algorithm that's used here is based on an algorithm called point feature labeling problem, PFLP. This is for 8 positions. So that will be the top right corner as the first position, the top left, and the third position is the bottom left, and the fourth position is the bottom right. And then right, top, left, bottom as the 5 to 8. So that's 8 positions freedom to choose the label. I hope that answers your questions. Great. Thank you very much. And this will be this will conclude my presentation, and thank you again for attending. Bye.